Have you ever just sat and watched the ocean? It's completely hypnotic, right? But what if I told you that in all that beautiful, endless motion, there's a story being told? A language that describes distant storms, the hidden shape of the seafloor, and the just raw power of our planet. Well, today, we're going to learn how to read it. You know, when you first look at the sea, especially on a windy day, your first impression is usually just chaos. It looks like a totally random, unpredictable mess of water, with waves crashing all over the place. It's beautiful for sure, but it doesn't seem like there's any real order to it. But is it really just chaos? Or is there a hidden structure under all of that? A set of rules that governs every single ripple and every monster wave? Well, that's the big question we're going to answer. Because it turns out, the ocean is speaking a very precise language, and we're about to become fluent. Okay, so here's the game plan. First, we're going to dissect a single wave to learn its basic parts. Then we'll zoom out and look at the entire family of waves, where they all come from. After that, we'll get into the dramatic showdown between deep and shallow water. And finally, we'll put it all together to see how you can read the waves in the real world. So, to make sense of the huge, complex ocean surface, we've got to start small. We need to understand the fundamental building block of it all, a single perfect wave. I promise, once we get this down, everything else starts to click into place. All right, this diagram here, this is basically our vocabulary list. Just like learning any new language, we've got to know the key terms. You can see the highest point, that's the crest, and the lowest point, the trough. We're about to break down 3 key measurements that tell us pretty much everything we need to know. First up is wave height. This is the one we're all pretty familiar with. It's just the vertical distance from the bottom of the trough to the very top of the crest. But it's more than just size. Wave height is a direct measure of a wave's energy. The higher the wave, the more punch it's packing. Okay, next up we've got wavelength. This tells us how spread out the waves are. It's the distance from one crest to the next one. Are the waves all bunched up and choppy, or are they long and stretched out? Wavelength gives us that answer. And finally, there's the wave period. Imagine you're sitting on a pier. The period is just how many seconds it takes for 2 wave crests in a row to pass you. You can think of it like the ocean's heartbeat, its rhythm. And as we're about to see, this is one of the biggest clues to a wave's history. So now we know how to describe a single wave. Let's see how this builds into the bigger picture. Because not all waves are created equal. They have different origins, different lifespans, and they carry totally different stories. Now, this is really cool. This chart shows the entire family of ocean waves, all organized by their period. Over on the far right, you've got the tides, taking a full 12 to 24 hours. In the middle, things like tsunamis. But look at that huge red mountain of energy on the left. That's where most of the action is. Yeah, that big peak of energy, with periods from about 1 second up to 30 seconds. Those are wind-generated waves. These are the waves we see at the beach, the ones surfers ride, the ones that rock boats. They are, by far, the most common waves on the planet, and they have 2 very distinct personalities. So on one hand, you have what's called wind waves, or sea. This is the choppy, messy stuff created by the local wind that's blowing right now. They're irregular, with shorter periods. But on the other hand, you have swell. Swell is wave energy that was born in a powerful storm, maybe thousands of miles away, days ago. As it traveled across the ocean, it got organized into these clean, smooth, powerful lines with long periods. Seeing a long-period swell on a calm day is literally like getting a postcard from a storm happening on the other side of the world. But a wave story isn't just about where it came from. Its journey takes a really dramatic turn when it finally gets close to shore. This is where the depth of the water completely changes the rules of the game. Now, the key thing to get here is that deep and shallow are relative terms. It all depends on the wave's length. A wave is considered a deep water wave as long as the water is deeper than half its wavelength. Its speed is determined by its own power, but once the water gets shallower than 1/20th of its wavelength, it becomes a shallow water wave. Now, its speed depends entirely on how deep the water is. And you can see exactly what that looks like right here. In deep water, the energy makes the water particles move in these perfect circles. But as the wave moves into shallow water and starts to feel the bottom, that circular motion gets squashed into these flat ovals. The wave is literally getting dragged by the seafloor, and that's what eventually makes it stand up and break. Okay, so let's apply this deep versus shallow rule to something absolutely massive. A tsunami. The wavelength of a big one can be an incredible 300 miles long. I mean, think about that. That's the distance from New York City to Boston, from one wave crest to the very next one. So what does that mean? Well, The deepest part of the ocean, the Mariana Trench, is about 7 miles deep. But for a wave with a 300-mile wavelength, 7 miles is incredibly shallow. Remember the rule: if the depth is less than 1/20th of the wavelength, it's a shallow water wave. Well, 1/20th of 300 miles is 15 miles. No part of the ocean is 15 miles deep, so a tsunami is a shallow water wave everywhere it goes.
And what does that mean for its speed? Well, remember, a shallow water wave speed depends only on depth. So in the extreme depth of the Mariana Trench, a tsunami can travel at over 700 miles per hour. That's the speed of a commercial jetliner, all because of that simple relationship between wavelength and water depth. It's just mind-blowing.
Okay, so this has all been really cool theory, right? But how does it actually help us read the ocean? Let's bring all this knowledge together and look at probably the most common way people try to decipher the ocean's message, a surf forecast.
Look familiar? The key factors in any surf report are the exact same concepts we just learned. Swell size, that's just wave height. Swell period is that rhythm we talked about, and a longer period means a more powerful swell that's traveled from a distant, powerful storm. Swell direction tells you where that storm was. And then local wind is like the final editor of the story. An onshore wind blows from the sea to the land, making everything messy. But an offshore wind blows from the land out to sea, and it grooms the waves, creating those perfect, clean conditions.
So here's the main takeaway. This isn't just abstract science. Whether you're a surfer, a sailor, or just someone who loves standing on the beach, you now have the fundamental tools to look past all that apparent chaos and actually see the underlying order. You can decode the story the ocean is telling you. Every single wave that arrives at your feet is the end of an epic journey. It's pure energy that's traveled, sometimes for thousands of miles, just to finish its story right there on the shore. Now that you know the language, what story are you going to see next time you watch them arrive?